Welcome to the next lecture, lecture number 27 of power system modeling. Here we are going to discuss the per unit quantities and systems. So in power system analysis, all calculation of impedances, current, voltage and power are done in per unit values rather than the physical values, that is ohm, ampere, kilovolt or kV. These per unit values are basically the scaled or normalized values. So all calculations will be doing on per unit value. So what is a per unit value then? Per unit value of any quantity can be defined. How do we define per unit values? So any quantity in per unit is the ratio of the physical value of the quantity by the base value of the quantity. So if we are dealing with the impedance, then the impedance per unit will be the actual value of the physical value in ohms of the quantity by the base value that we have taken for the system. Now, if we are going to take the per unit value of the current, so similarly the per unit value will be the physical value of the quantity in ampere divided by the current base, and same for the voltage as well as the power. So here we can see that the per unit quantities are the dimensionless quantities because both numerator and denominator will be of the same dimension. So same units, and thus it is a dimensionless quantity. Now what are the advantages of per unit system? Why do we want the actual values to be converted to per unit system? Now the network analysis becomes simpler as all impedances can be directly added together regardless of the system voltage. So whatever might be the system voltage, you can directly add all the impedances together. So this is one of the important advantage of per unit system. The next advantage is that it will eliminate the factor 3 or root 3 which is appearing in the multiplication or division for converting the three phase to single phase, generally associated with star delta quantities, as they are directly taken in the base quantity. So once the base quantities are defined, you no longer want to use the quantities 3 or root 3. Third is that usually the impedance of electrical apparatus is given in percentage or per unit values by the manufacturer on the nameplate rating. So whenever we are purchasing any instrument, we see there is a nameplate rating, and in that nameplate rating the impedance values of the apparatus will be given in per unit values. Fourth advantage is difference in operating characteristic of many electrical apparatus can be estimated by a comparison of their constant expressed in per unit values. So if we want to compare too many electrical apparatus with difference in their operating characteristic, they can be compared by comparing their per unit values. Next advantage is per unit impedance of machines of same type or widely different rating usually lie within a narrow range, although the ohmic value differ widely for different ratings. So whenever we see machines whose ratings are different, then their actual value may be of quite difference in their ohmic range, but when they are converted to per unit values, they lie very narrow range. And per unit quantities are more convenient in calculation using digital computers. So nowadays all digital computers will be using the per unit values to calculate any problems on the power system. So first we will see for a single phase system how do we obtain the per unit values, and then we'll go for three phase system. So basically there are four quantities. One is known as the voltage, other is the current, and the power in volt ampere, and the impedance. So these four quantities we have to define any two among the four quantities. The other two can be easily determined. So out of the four quantities, the two quantities has to be defined. The other two quantities will be easily determined if we know the two quantities. So two quantities will be determined. So what are the four quantities? It will be voltage, current, power and impedance. So this power is basically taken as complex power. Okay, this power is taken as complex power. So base value is selected such that the system voltage is normally close to unity. So there is a way by which we are choosing the base voltage of the system. So base voltage is chosen so that it is equal to the system voltage. And base power, that is in volt ampere, is usually selected in the kVA range or MVA rating of any one of the machine or transformer, or it is convenient if you go with the digit 1, 10, 100 or 1000 MVA depending upon the system size. Now let us derive one by one. So these three quantities, let us take the current IB as the base current, VB as selected base voltage, and SB is the selected volt ampere, that is the power base. Now we know that the current is basically power by voltage, and here we take the power in terms of the complex power. So base current IB is equal to the base power divided by the base voltage. Then the base impedance ZB will be the ratio of base voltage by base current. Now the current we can substitute from the equation 1 to here, then it will be written in SB by VB. So we get ZB as equal to VB square by SB. Then we have to remember this formula. So the base impedance is basically equal to the KB base square divided by the MB base. So Z base, that is the impedance base, is equal to kilovolt base, that is the voltage square, divided by the power. Power in complex power is the base quantity. So base quantity is always a real number. So whenever we are taking any base quantity, we should know that the base quantity will always be a real number. However, the physical quantity can be complex. Like suppose we are taking S. So S is equal to P plus JQ. So this is a complex quantity. So the actual complex power is complex in nature. However, when we take SB, then it will be a real value. It will be a real value that we are going to look at. So SB, that is the base power, is equal to volt ampere base is equal to PB equal to QB equal to VB into IB. So PB is the real power, QB is the reactive power, and the product of voltage base and the current base will give you the power base. Now the base power for the real quantity or the imaginary quantity is equal to the complex quantity, and it is the product of voltage and current base. Similarly, the impedance base ZB is equal to the reactance or the resistance base. So as we write Z is equal to R plus JX. So whenever we are taking the Z base, we have to take is equal to the reactance base or the resistance base. Then the admittance base will be equal to the susceptance or the conductance. It is the reciprocal of the current by voltage base. Then Z per unit. So we know that the per unit value is equal to the actual value of the quantity divided by the base value. So here the first quantity that we are going to take is the per unit Z value, that is the impedance. So Z actual by Z base, and we know that the Z base is equal to kV base whole square divided by MVA base. So here if we substitute this and the actual value is Z actual, so we get the Z per unit is equal to Z actual multiplied by MVA base divided by kV base whole square. Now the next quantity current per unit is equal to actual current by base current. Per unit value of voltage will be actual voltage by the base voltage. Then the power in per unit system, that is the volt ampere per unit, is the actual value divided by the base value of the power. So the per unit value of the impedance can be written by divide actual value of the impedance divided by the base value. So we have known that the actual value can be complex. So actual value can be complex. However, the real base value will always be a real quantity. So base value will be always a real quantity. So Z per unit will be then Z per unit angle theta, which is equal to R per unit plus J times X per unit. So R per unit, whenever we are calculating actual value of the resistance, now here we have to make a special note. We are not dividing with R base, rather than we are dividing with Z base. Similarly, in X per unit, the actual value of the reactance, now here also special note, we are dividing with Z base rather than X base. Now the complex power in per unit S per unit is equal to P, that is the real power in per unit, plus J times the reactive power in per unit. Whereas the real power in per unit is the actual value of the power. Now make a special note, here it is S base. Similarly, the reactive power in per unit is equal to the reactive power actual value divided by, make a special note, here it is the complex base. So both here in the resistance calculation as well as reactance calculation, we take the Z base, and for power calculation P and Q, we take the complex base. Now, if we are dividing the actual value of the power S angle theta divided by the base power S base, and S angle theta can be written by V I conjugate, and this can be further break up into the angle and magnitude format, and S base can be written as VVIB. So we can easily obtain that S per unit is directly V per unit I per unit conjugate. So we know that S is equal to VI conjugate. So similarly, from this we are getting S per unit is equal to V per unit into I per unit conjugate. Now, how do we convert the per unit values to the physical values? So, if we know the per unit values of any quantities, whether it is a current or voltage, if we multiply it with the base current and base voltage, we get the actual value of the current and the actual value of the voltage. The value of Z, R and X, the base value will be constant, that is the Z base, and then we are multiplying with the Z per unit, R per unit and X per unit. However, the Z base is constant. Similarly, for power, we have the complex power SV as constant, and then multiplied with the per unit value of the complex power, real power and reactive power, we are getting the actual values of the PQ and S. Now, how do we analyze analysis of a system? So first we take the base quantities defined. Either we are defining the two base quantities, one is power and the voltage, then we can derive the current and the impedance base, and the practical unit values of all this, that is the actual value we give, convert into per unit realization, do all the analysis, and then back transform it into the actual values by multiplying with the base value. So here, if two base quantities are given, other two base quantities we can obtain. So total there will be four quantities, and these four quantities are the actual quantities. So all this per unit realization and analysis will be done and transformed back to the actual values. Now we will be requiring to change of base for the entire power system. Why do we require that? Generally, the per unit impedance of a given apparatus is given on the base of its own volt ampere and voltage rating, and consequently on the basis of its own impedance base. So whenever we have some equipment, so if we have an equipment alone, then the per unit values of the impedance of that particular equipment will be obtained on the base value of the power and the voltage rating. Base value of the power and the voltage rating. And on the impedance base, we are obtaining the per unit values. When such an apparatus is used in a system that has its own base, it becomes necessary to refer all the given base to the system base. Now, so many equipments are connected. Suppose so many equipments are connected to form a power system network, then we require that each equipment should be connected to form for a system base. So here there will be a system base to which all the base values of the equipment will have to convert into the system base. So assuming the per unit impedance of the apparatus is given on the basis of its nameplate rating, we can obtain the Z per unit of the old base to the new base. So you have the Z per unit given is equal to Z actual, because you have the actual value multiplied with the base values. Base values of the MVA base given by KV base given square. So this ratio is basically coming from the Z base. We know that it is equal to KV base whole square divided by the MVA base, and the per unit value is equal to actual value divided by the base value. So we have can obtain this Z per unit given. For the new set of voltage and volt ampere bases, the Z per unit new will now change. Okay, and this is again obtained as equation number 2, and that was equation number 1. Now if we divide it, we can obtain the Z per unit new is equal to Z per unit old or the given into the ratio of the power term multiplied by the voltage term. So this is the power term and this is the voltage term. Now the power term, if we see it, so it is MVA base new by given, new by old or into given by new, that is the voltage base square. So this formula has to be remembered in order to convert one base to the other. So Z per unit new is equal to Z per unit given multiplied with MVA base new by MVA base given into KV base given by KV base new whole square. So in this way we can obtain the base changing from the old base to the new base. Now the per unit of a three-phase system. So we have seen the single-phase system. Let us see for the three-phase system. We know that if a system is balanced, all the three-phase system can be analyzed on the basis of single phase. So the current base can be written in the form of power base divided by the voltage base. Now if it is a single phase, then the power will be single phase power. Then here the voltage has to be taken in line to neutral. Now if we take the power in three phase quantity, then the voltage has to be taken in line to line format multiplied with root 3. Now similarly Z base will be equal to voltage by current. Now here all these analysis are done in single phase quantities, so it has to be line to neutral voltage. Then it will be converted into kV base line to neutral by MVA base single phase. So this MVA base has to be single phase, not three phase. So if you are taking the MVA base three phase, then instead of line to neutral voltage, we will be taking the line to line voltage. Now we know that for a balanced system, voltage base line to neutral equal to voltage base line to line divided by root 3, and the power S single phase equal to three phase by 3. So these concepts we are using to convert any three phase to single phase or single phase to three phase, and on analysis are being done on single phase quantities and back transform into three phase system. Now since the transformer is changing the level of the voltage in the power system, it is important to see the per unit representation of a transformer. Now a three-phase transformer forming a part of a three-phase system can be represented by a single-phase transformer in obtaining the per-phase solution of the system. We know that in a power system, three-phase transformers are generally used. However, the single line diagram, we do it for single phase. So three-phase transformer can be represented with an equivalent single-phase transformer. The delta connected winding is replaced by an equivalent star. So this is an important point. Whenever you have a three-phase transformer and you want to convert into single phase, then the delta connected winding has to be converted into star connected, so that the transformation ratio of the equivalent single phase is always line to line voltage ratio of the three-phase transformer. So whenever we are solving any problem based on the transformer and we want to convert the three-phase transformer to single-phase transformer, we have to check whether the connections are in the form of star delta, delta star, or any other calculations, any other connections. So all this delta connection network has to be first converted into star, and then only we have to convert into single phase, because the transformation ratio is very important term in single phase quantity, which has to be in the form of line to line voltage. So here let us see. So this is a single phase transformer whose turns ratio is 1 is to A. ZP is the primary winding impedance and ZS is the secondary winding impedance. V1 is the voltage of the primary winding, V2 is the voltage of the secondary winding or the load voltage. So here we are connecting with the load. I1 is the primary current and I2 is the secondary current. So this is a single phase transformer. We want to convert this transformer into per unit value. So if you want to convert this transformer into per unit value, the voltage will be converted as such V1 per unit, the current will be converted as I per unit, and this ideal transformer will be replaced uh, in the per unit equivalent circuit of a transformer with a single impedance Z per unit, and here we have V2 per unit. So here we see that the circuit of a transformer when converted to per unit values is quite simple as compared to the actual transformer. So there is no ideal transformer. This ideal transformer is replaced here, and this impedance ZP and ZS is replaced by with only one impedance. So we will look into this. So if we choose the volt ampere base and the voltage base on the two sides of a transformer in the ratio of transformation, we know that this is the formula for the relationship between the voltage and the turns ratio. So V1 base by V2 base is equal to 1 by A, because you have a transformer which is in the ratio of 1 is to A. Then I1 base or I2 base will be equal to A. We know that the current base is inversely proportional to the voltage base as the power is common. So the impedance base will be equal to V1 base by I1 base, that is the impedance of Z1, Z2 secondary voltage base by current base of the secondary voltage and secondary current, and we know that from the KVL equation V2 is equal to V1 minus I1 ZP into A times turn ratio minus I2 ZS. So if we multiply this V2, we can write it in the form of V2 per unit multiplied by into V2 base. Similarly, V1 can be written as V1 per unit into V1 base. I1 can be written as I1 per unit multiplied with I1 base, and ZP can be written as ZP per unit into Z1 base multiplied with A, that is the turns ratio, and again I2 and ZS can be represented with another two format. So here we can see that the V2 per unit is equal to V1 per unit my I1 per unit into Z per unit minus I2 per unit into ZS per unit. So using these notations of earlier things, we can get this equation V2 per unit is equal to this ratio. So here we have the current in this format I1 by I2. So if we take I1 by I1 base equal to I2 by I2 base, this means I1 per unit is equal to I2 per unit equal to I per unit. That is the meaning that there is only one impedance, that is Z per unit, for the entire system. So here you have V1 per unit and here you have V2 per unit. So current per unit is same, it means only one current is flowing through the entire system. Similarly, V2 per unit, after calculations we will get V1 per unit minus I per unit into Z per unit. This is the KVL equation of a single loop. So it represents a simple equivalent circuit without ideal transformer. So whenever we have some representation of a transformer, we have an ideal transformer that is vanishing whenever we are converting it into the per unit system. Thus, considerable simplification has been achieved with per unit method. So whenever we are converting into per unit method, ideal transformer vanishes and Z per unit can be determined directly from Z equivalent either on the primary side or the secondary side. So Z1, that is the primary circuit impedance, equal to Zp plus Zs by A square. So this has been converted to the primary side. So Zs by A square means the secondary impedance is taken to the primary side and the equivalent impedance is taken from the primary domain. So if we are dividing with Z1 base all these things from the LHS side and the RHS side, so we get Z1 per unit is equal to Zp per unit plus Zs per unit, and this is equal to the total impedance, means the primary per unit and secondary per unit impedances are directly added up to find the per unit impedance. If this has been done on the primary side, if we are doing on the secondary side in the similar nature, and the primary impedances is converted to secondary impedance and add up and divide with Z2 base on the LHS and the RHS side, then we get Z2 per unit is equal to Zs per unit plus Zp per unit equal to this. So whether we are going from the primary side or the secondary side, we see that the Z1 per unit, that is the total impedance referred to the primary circuit or total impedance referred to the secondary circuit, remains the same provided the voltage base on the two sides are in the ratio of transformation. So this is one of the important advantage of converting it into per unit system. We can deal with either the primary circuit or the secondary circuit or the transformer, and we can remove the idle transformer. So this completes the per unit system. Thank you.